watching us. And just to remind you that today the GNSS principle and its application, which will be presented by Dr. Shian from the Regional Center of Space Science Technology, Asian Pacific, and Behang University, cooperation with the Regional Center for Space Science Technology, Jordan. And actually, it is organized with cooperation with many organizations and scientific societies all over Arab world. And please allow me to welcome you and thank you very much for your attendees. And please, Mr. Shian, you can start now.
Okay, good afternoon, everybody. So let's continue for our lectures. I will share my screens. Okay, give me permission to share screen. I need permission to share screen, Dr. Tony.
You are permitted, yeah.
Could you give us a permission? Please give me a permission to share screen.
You are permitted.
Now you are permitted. You can actually share your screen. It's no problem.
No, it's just prohibited. Please check for permission again.
Ibrahim?
Yeah, yeah, now?
Is it okay now?
Oh, okay now.
Okay, that's fine.
Great. So in today's lectures, I will talk about the GNSS receiver. So we have talked about principles, something, and we will talk about how to make a receiver. So I will talk about like for example, the architectures, architectures, front end, acquisition tracking, and parameter and calculations, and so on. So so when we talk about the receiver, to make a receiver, the receiver contains many parts. For example, we show that here the radio. The first part is called the radio frequency part. It's and a very high frequency. For example, the GPS example, the GPS, whatever GPS or BDS, they are frequency about 1 gigahertz to 2 gigahertz. So it's a very high frequency. According to signal processing theory, to do this, you need a very good front end. So we need the called radio frequency part. We will have an antenna, we will have a front end converter. I will talk a little bit later. And then the second part, in the yellow parts, is acquisition and tracking here. Acquisition and tracking. So this one will give you to find the detailed satellite. Where is the satellite? Then you need to find it. And the third part is about navigation parameter calculations. We show here navigation parameter calculations. So these parts will make the receiver to detail calculation. For example, the data, the positions, etc. Okay, so so this is a typical of a GNSS receiver. We need antenna, and remember, commonly the eye from focus the signal at gigahertz. I'll show here at the gigahertz, and the baseband. Okay, the baseband commonly it's integrated to a chip, so it's focused on megahertz to kilohertz signal processing. This one, this is we call baseband. Commonly, when you buy a cell phone, then the signal processing part is inside the cell phone, And the last part is application platforms. It gives you the result to your processor. It commonly gives output, the results at hertz level. So this is typically the architecture of a receiver. Different parts, different chips are working on a different frequency. A typical receiver is actually a combination of lots of chips. Okay, traditionally we will have some chips. For example, there's a chip from Xilinx, and you have a correlator. This is a front end. So this one is at a gigahertz level, and this one is at megahertz level. Okay, so megahertz level, and this is a RISC processor. This is at a hertz level. Okay, so typically a receiver is contain a different chip made of different chips. So we are also trying to integrate nowadays. We are trying to integrate all these chips into a processor. For example, if you buy the cell phones, whatever from Huawei or whatever Xiaomi or whatever from some Samsung, okay, the core chip of them is maybe from MTK, maybe from Qualcomm, or maybe from Hisense. So all these chips I mentioned here, gigahertz, megahertz level, hertz level, all are integrate into the CPU, actually, the processor of the receiver. So nowadays we seldom see, for example, there was a chip for receiver, there was a chip for GPS, the chip for Beidou. No, nowadays all this receiver was put inside the processor of the cell phone, but still the processor in the cell phone, the GNSS receiver in the cell phone is not working as a very good performance. It is because there was quite many limitations of the chips. For example, the processing capability, for example, the memory, the many limitations. So what we need to do is to increase the performance of the cell phone. Then we can increase the performance of the GNSS receiver inside it. As well as the other, we have models. We have lots of devices which has very high performance receiver for GNSS receiver, for example, for surveying and for other applications. It's individual receiver, then we have a better performance. Before we talking about this architecture, okay, the main specifications, for example, if you buy something, then you need to open the book, open the specification to read the documents. So mainly the GNSS specifications contains the following parts. The first is generally we need to talk what frequency the receiver is received and how many channel numbers, whether it decodes about calls acquisition code or maybe military code. And for accuracy, we are focused on the position, velocities, and time accuracy. And for the first time to fix, we focus on cold start, warm start, and hot start, and some dynamic and other functions. Let's give you some examples. The main, actually, when you open your cell phone, commonly it needs maybe, I don't know for your experience, commonly sometimes it's very fast to make a position. For example, if you open your cell phone, sometimes it gives you position very quickly. But sometimes when you open your cell phone, it's as a positioning, and wait a lot of long time, very long time, maybe several minutes, you cannot find a good fix. So what's the reason? So in order to get the performance of the time to fix, we call this start time or TTFF. For example, and then this one, start time. Because start time or time to first fix. This means how much time has elapsed between the power on or startup of the receiver to make a first fix. In order to make a fix, the receiver need to have full information. For example, they need to know the orbit information. They need to know where is the satellite. So the terms cold or warm or hot start means how many information you already have. The cold start means if the receiver is not used for a very long time, or maybe moved several hundred kilometers away in other different countries, the receiver may not know the current automatic. They don't know the current orbit. They don't know the current ephemeris. They don't have time or position information. So it will take a very long time to get the first fix. But the warm start means you know something. You know the current orbit information. You know your position, and maybe the time. That all valid. So what you need is to get the recent orbit information and precise time and previous time. So it's some part of information is valid, so it's called warm start. But for the hot start, means everything is about the orbit, about the time. You know almost everything. So the hot start means you just turn off and then you turn on. So commonly in hot start, the receiver will boot very fast to get your first fix. But in cold start, maybe a very long time. So it's a very important specification in the receiver. Let's, for example, this is a receiver called, it's a very old version, the Falcom GPS receiver JP3. Okay, for this version, Falcom GPS JP3. Okay, we will see from January. You may see from January, you will get a result of frequency. Okay, the frequency is, what's the frequency? You may see frequency, sorry, frequency at L1. L1 means it's received the GPS L1 signal at 1.5 gigahertz. Okay, this is for the GPS, so this is frequency. And the code is that is CA code. You may see CA code. Okay, CA code is the course acquisition code. It's just for for civilian users, and also for channels. The channels, for example, the 12 channels. It means at maximally you can receive 12 satellites at the same time. You can process in 12 satellites. So why we need 12 satellites? Why 12 satellites? So let's, for example, for 12 satellites, that means you, for example, the GPS has only about 32 satellites. The GPS totally, sorry, some mistake. Totally 32 satellites. So if you see only half of the Earth, you will see 16 satellites. And then you look some parts. For example, if you are here, you can look something above this one. So commonly about no more than 12 satellites. For example, in Beijing, commonly we will see about 8 or 9 commonly satellites. So 12 is enough for most cases. And for accuracy, a receiver, commonly a receiver is about 10 meters, approximately, about 10 meters. If without selective availability, 10 meters. And the velocity is commonly about 0.1 meter per second. And for time, it's 1 microsecond. But if you're using differential GPS technologies, and a differential. You can eliminate some errors from such as ionospheric errors and tropospheric errors, so that the accuracy can increase from 10 meters to commonly about 1 meters typically. Okay, so if you're using differential GPS technologies, for example, by a call station, you will much improvements in accuracy. And for the acquisition, commonly this we also call the TTFF. We will give you about, for example, if you cold start, just start, commonly nearly 1 minute. But for warm one, about 38 seconds. But for hot, only a few seconds. So that is how knowledge information you have, you will speed up for your receiver. And also for dynamic, for example, here, dynamic. Commonly, a receiver has a limitation of altitude less than 18 kilometers. If you buy a chip, commonly a chip, they will tell you so the maximum altitude of the receiver commonly was limited to 18 kilometers. Remember the GPS, the height of the GPS satellites, the satellites. Okay, this is satellites. Commonly, the height is 20,000 kilometers. So actually, sorry, 20. So actually this is only, I think probably at here, very very near to the Earth. Okay, so this is 18 kilometers. Okay, so why we have such limitation? The altitude of a receiver has such limitation. It is because the regulation policies commonly from the United States. So if you buy the chip from, I think probably from buy a chip from United States, commonly you will get a limitation of the maximum height you can use, as well as the maximum velocities. Okay, this one, 515 meters per second, the maximum velocities you can use. Okay, this two is the regulation coming from the US. Probably if you buy a chip maybe from European, is similar, but if you find maybe from Russian, probably don't have such limitations. It's not from theoretically limitation, it's just from the political policies, the expulsion limitation. Okay, and then commonly a receiver will tell you they will have, you can use for some acceleration at 4G maximum, and the jerk at, for example, this case is 2G per second. And also the receiver can have the power and the serial pulse output and so on. So this is commonly a specification of a receiver. So when you got a receiver, commonly because you also receive the GPS signal as well as this receiver. So commonly you will get a similar, performance in these chips and your chips. So all the performance will be quite similar. Okay, so when the receiver makes output, commonly we use NMEA protocol. NMEA protocol. It's from the United States called the National Marine Electronics Association. It's made by association. So all this information is output by a text mode, by text mode. Okay. So you just tell, for example, the GLL will tell you the latitude, the longitude, and the time. And for RMC, will tell you position and the speed, so on. They just use text to give you an output of the result. Also, someone will also get some message to tell you the different results. So you're using for the human UI interface, human machine interface. Actually, it's this device will read the data from a GPS via AME protocol, and then they will display the results in the UI interface. The GPS just output all this information by NIM protocol. Commonly, a receiver, when you make a receiver, because according to the different purpose, the receiver can be divided as a soft receiver. The soft receiver is a receiver that the main part of the receiver is implemented by the software, which running on DSP or PC or other general purpose processors. So nowadays it's very easy to make flexible, to make deployments, but the performance is not so good, especially for the high signal processing performance. The performance is, you need a huge power. And some receiver is a high sensitive receiver. It's used for the weak signal environments. For example, in a room, a forest, a city cavern, and even in high Earth orbit spacecraft. The key technology of this kind of receiver is to how to pick up the weak signal from the very high level noise. It's mainly by signal processing technologies. And the next part, next receiver type is called high dynamic receiver. The high dynamic receiver mainly used for fighter and missiles. And the key technology of this kind of receiver is how to solve the problem mainly by the Doppler introduced by the speed, acceleration, or jerk. So during the highly motion environments, and the frequency will be jumping very quickly. So how to keep up with the signal from the high dynamics, which is totally different from the problem of pick up signal from the high level noise. And the next part is type is multi-system GNSS receiver. Nowadays, the receiver, for example, the receiver itself is try to integrate 2 or more GNSS systems together, such as to integrate the GPS, GLONASS, BDS, and Galileo and other augmentation system together, just into one chip or one receiver. And the last type is about the receiver for mapping or survey. So it is a very sophisticated receiver. It's only for professional users, like in agriculture, mapping, and GIS, etc. The principle of this kind of receiver, they will focus on how to get high accuracy, and they often store enormous amount of data, and then they can process the result a little bit later. You can process data, even you store in your machine and post-processing it, just for get high accuracy. I will give a lot of detailed applications in later. Okay, so when we talk about to make a receiver, we need to talk in detail about these parts. So the first is about the radio frequency parts. The radio frequency mainly contains 3 parts in the receiver. One is antenna, the second is RF front end, and the digitalizations. Okay, so commonly a receiver, detectors, they're called hypergeneous receiver. Commonly they will have the following parts. They have a features, they have a mixture, and amplifier. These three things is very important. The filter will filter out the signal you don't want, and the mixer will decrease the frequency from maybe from gigahertz to megahertz level, so it make you can process it. An amplifier is used because the signal is very weak, so we need to amplify the signal to be large enough to let our sensors, mainly ADC, can process it. And after these steps, you will get IQ results from the receiver. Okay, so let's look in detail the requirements of the radio frequency parts. So for input signal, when the satellite, okay, they transmit the signal down to you. Okay, typically the input signal, the satellite input to you, this means that here the signal strength is -13 dB milliwatt. This is a unit. It's likely to be 0.1 femtowatt. I think, do you know watt? Watt is the power unit. So 0.1 femtowatt. I think probably if you write this one, you will get 0.00656 1 2 3 5 6 7 8 9 10 11 12 okay 13, yeah, sorry, 13 sorry 13.1 watts, probably something like this one, I'm not sure. 1 2 3 4 5 6 7 8 9 10 11 12, okay, fine, great. This is horrible, right? It's very hard to write, so in mathematically we use -100. Okay, sorry, this is mistake. It's milliwatts. Okay, milliwatt. We use mathematical abbreviation of -130 dB milliwatt to represent this information, corresponding to 0.1 femtowatt. Okay, this is the signal you will receive. And for the signal, the bandwidth is 2 megahertz for the C code. Okay, so we'll see noise floor, because you will not only receive the signal from the satellite, but also you will receive a lot of terminal noise. Like this one, noise. Okay, for this noise, when you receive this noise from maybe from the terminal noise. Okay, this noise commonly is -110 dB milliwatt. So this is corresponding to 0.0000000000001 milliwatts. Oh, horrible. Again. So which one is stronger? Actually, this one is more strong. So that means the signal power is much weak than the noise, and about 20 dB more, corresponding I think to about 100 times more compared to the noise power. The signal is only 1% of the noise. So what you do, I think it's a very amazing thing, is you will try to pick up the signal about 100 times lower than the noise. Make an imagination. You maybe listen to the FM. Okay, you will see that's music, blah 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 blah, and the very small the noise. I think for you it's very easy to understand the meaning of the speech or maybe the music. But if we change the way, for the GPS receiver, what they are doing, what you receive, the noise is, but the music is very small. But what you need is to extract this information under the noise. Okay, so that is the challenge. So what you need to do is to make the gain by the signal processing technologies in the receiver. Okay, so what you need is to amplify the signal at first to let the signal can receive it. Commonly, our digital chips, for example, the ADC, need a PP voltage to be 1 to 2 volts. So that means you need to amplify the signal for about 100 dB more. This is correspondingly to about, I will show you, 10 to 11 times more, about 100,000,000,000 times more. The signal need to amplify at a very big the gain. And also you were using signal processing technologies by code correlation to provide additional 43 dB gain to the signal to let you process it. So this is typically the requirement of the I front end. Okay, and for the antenna, commonly the GNSS antenna, they will tell you they will have a center frequency. That means it will receive the signal at this frequency, and the polarization of the signal is the right hand circular polarizations. It's quite technically, and commonly I want to show you that most interesting is the gain of the receiver at 10 degree elevation. Is the gain is -1 dB, but the gain at the zenith, is +5, but the gain at this one is -1. That means the satellite above your head, this one will have 5 dB more gain compared to the satellite at your floor. This one will have -1 dB gain. Okay, so what I want to tell you is this one, the satellite above your head, commonly they will have better accuracy and better performance. Okay, this is a very cheap antenna. Commonly, I don't know the price at maybe Jordan and other countries, but in China, commonly we buy these antennas from price about maybe $2 US, maybe $1 US about this price, very cheap. But this antenna, that we call high performance antenna, will be much more expensive for the high, we call this high performance receiver. High performance antenna. Okay, for example, this is from the Trimble antenna. They will have very high gain, about 30 to 50 dB gain. And this is from Topcon. Inside they have choke ring. They will have very better performance for anti-multipath. And for this antenna area, they have the performance anti-jamming. Okay, this is a lot of different type of high performance antenna. This will give you more better performance for the receiver. For example, for anti-multipath, they will give you more accuracy results. But this antenna will be quite expensive. For example, we just bought an antenna from Trimble, and the price is about, I think about nearly $5,000 for one antenna. 5,000 US dollar. Maybe some of them is 3,000 US dollars. Some is about 5,000 US dollars just for one antenna. So, but it's very high performance. Okay, so this is the eye front end. So here you will see the diagrams of a receiver. Commonly, you will you need to get the antenna, and you will have the amplifier and the synthesis actual mixtures and the filters, and this is filters, and this is filters. Okay, it's amplifier. This is mixture. Actually, the chip inside it is made of this electronic chips to make the receiver, and then to make the digitalization. For the digitalization, I will say something, because when you receive the signal, when you receive the GPS signal, commonly it's the GPS signal. It's just the signal of a sine or cosine wave with data modulated on the face by, for example, the BPSK modulation. It is analog one. Okay, but if you want to receive the signal, you need to make it to digital, to let it to be this one to be digital, because it's digitalization. Okay. In the GPS, commonly we use 102-bit ADC. This is for the GPS, 102-bit ADC. It's enough for the receiver, because the receiver the signal is lower than the noise, so very low bit quantization is enough. But if you commonly for the mobile signal processing, for sensoring signal processing, maybe you need the 10-bit or maybe 12-bit ADC. But for the GPS, only 1 or 2-bit ADC will be enough. And the next part, in the receiver, I will tell you about acquisition and the tracking technologies. Okay, this is acquisition and tracking here. I will show you. My pen. Sorry, where's my pen? Okay, here. Okay, acquisition and tracking here. So this is acquisition and tracking. After here ADC, the things become digital. So the acquisition tracking is to process the signal. It's used to process the digital signal. So for the first is acquisition. The acquisition means how to find the satellite. For example, when you open your receiver, you don't know which satellite is on your head. You don't know where is it. You don't have any ideas about the satellite above your head. So what you do is to search which satellite is visible, to search the visible satellite, to find where is it. During the search, it's neat. It's similar to you open the other's door by the key. So you need to find where is the code face. Where is the code face? And what is the Doppler? Remember Doppler? Because the satellites move, so there will be Doppler. Ooh, maybe the signal, maybe you send the signal at ooh this time, ooh, but during the movement of the satellite, sometimes the signal will be ooh, or maybe sometimes it will be ooh. So it's the Doppler frequency. So we need to search the frequency. The frequency may be this is the frequency range for the 10 kilohertz annual. and for 500 hertz at each search, and for code, there is about 21 possibilities. And this one for code, for example, if you open a keyhole by your key, you need to step by step, chip by chip, tick by tick to open the door. Similar as the GPS, it needs to search the code for the half chip step. So totally they have 1023 chips plus half. This is 2000 probabilities. So in this range, you have 2000 probabilities, and totally for 32 satellites. So the totally search probability of the search, you need to search, in order to find the satellite, you need to do is to search 21 times 2046 and times 32, and currently this is more than 1 million possibilities. So it is quite amazing. It is quite amazing, right? Only when you search for whole 1 million possibilities, you will then know which satellite is above your head. And this is the objective in the searching acquisition step. So acquisition is to find the probabilities. For example, at this 1 million probabilities, you will find, you will see here, sorry, it's just connection problem, right?
Dr. Jiang? Dr. Jiang?
Okay.
Okay.
Yeah, just maybe connection problem.
Okay.
Okay, I will continue. Is everything fine? Is
Yeah,
my voice fine?
Yeah, fine.
Okay, so I will repeat again. Only when you do the totally 1 million search, you will know where is the satellite, which satellite is on your head. Okay, so what we need to do is search for this region and find the peak. Only you have the right code phase and the right Doppler, you will find this peak. Only everything is correct, you will find the peak. The acquisition is to try to find this peak. And if there is no signal, you will see something noisy like this one, noisy. But if you with the signal, you will see the peak. Okay, this is to find the satellite. So okay, so what we do is to just to find the satellite in this area, the L1 frequency. And this is what we find in cell phone. Similar ways can be done by searching for L2 and L1P and L2P signal. Similar, you can do the same thing. And the signal commonly, this is signal actually, this signal is commonly negative 20 dB to the noise floor commonly. So we need to do is find this one. In order to find it, we need some criteria. Commonly, we call it a Newman person criteria. That means we will set a threshold, commonly the gamma here, where there is threshold here. If the correlation with power is larger than this one, we think it is signal. If less than this one, we think this is noise, and we think that this is signal. This is signal and this is noise. So commonly we call Newman-Person criteria. It's used commonly within we can tolerate 5% error, and we can set a threshold. And the acquisition step commonly can be divided by search steps, different search methodologies. The first is to serial search. That means to search face by face, Doppler by Doppler, step by step. And some is parallel search. For example, we can use the Fourier transform to search for one frequency, a series of frequency at the same time by the Fourier transform, maybe discrete Fourier transform at the same time, at one group signal at the same time. So commonly it's need 2064 probabilities for each search. And also we can do parallel for code search by using the convolution methodologies. Where we use the FFT, the fast Fourier transform and the inverse fast Fourier transform, and only to do the search as the 21 possibilities. Okay, with different methodologies. And after make acquisition, then we will know where is the satellite. And then after acquisition, we will know the satellite. For example, you are here, and you are here. But then, when we need to communication with the satellite, we call tracking. But consider the satellite is moved. So this may introduce a problem that because the satellite is moving, so the frequency is always drifting. I think maybe you have experience. For example, if you listen to FM radio, sometimes the frequency maybe is a little bit drift. What you need to do is to tuning the frequency to let the signal to be good enough. But probably it's zzz, but you need to tuning it. But for the GPS, commonly, for example, we have 12 satellites above your head, so it's not possible for you to have 12 hands to tuning each frequency, each satellite. So actually, this tuning form is done automatically by the computer, or maybe by the chips. We call it tracking loop. Okay, the tracking loop, the purpose of the tracking loop is to keep the signal we will check it, to keep it to be not lost. We need to tracking the code phase by the DLL, and to keep up with the carrier frequency and the carrier phase by the phase lock loop and frequency lock loop. What we need to do by this one. This is the tracking loops. For the phase lock loop, and commonly we will make by the following parts. The first is a detector, and you will know how much the error it is by phase detector, and then we will use for a filter, and then turn back. So we call it a loop. The first one is find how much the error is, but because the error will be frustrated, so we make a filter to let it be to make stable, and then tell the adjustment to the oscillator and make adjustment to corresponding new signal. So this is called the phased lock loop to keep up with the phase information of the signal. Okay, so the filter can be designed with different formats. For example, the first order filter, second order filter, and third order filter. It is used to keep up with different type of the dynamic objects. If for a user that is quite stable, you can use first order with a little motion. For example, the car, the bike, or maybe people it's walking, you can use second order. But for the object that has about very high dynamics, you can use third order loops. Okay. So ignore something. So for example, this is the phase lock loop. For example, you may see that this is the true frequency of the signal, and at first maybe you have the error, and then gradually, okay, you will finally keep up with the right frequency. And this is the noise. This is the noise, the green one, and this is the filtered results. That means if I have noise after filter, it's quite smooth. And also, this is the output of the data. You will see the output of the data. This is commonly this from the error diagrams. It's quite good error diagrams. And also, you can keep up the with the carrier frequency. For example, the frequency lock loop. You need to keep up with the frequency. It's similar as a PIR, the phase lock loop, but it just keep up the frequency. A very good note. And for the code tracking, you will use the we call delay lock loop to keep up with the code information. So it's quite difficult because it is a digital signal processing part. So by using DLL, delay lock loop, the PLL and FL, we will find the right phase plus code. So that means the satellite, if the satellite is moving, so we can still keep up with the signal. Okay, this is delay lock loop. So after you keep up with the signal, you will see the signal will be keep up like this green one. They will keep tracking it, and you will get a very good diagram, error diagram. But there were some errors about multipass effect. It's a very big error in the cities when you're using the GNSS receiver. For example, this is called multipass. That means the signal, they have a direct signal. This is called LOS, line of sight. And another one is by a reflected way. So these two satellites will finally sending both to the receiver. Then for the receiver, you will find your result is the combination of the two signals. Theoretically, you will get a triangle curve, and this is the maximum in the line of sight signal. But because you have here, I see here you have a multipass, so it will make the curve have a slightly distortion. It makes you very hard to distinguish the right one. So finally, they will introduce error to the tracking. Commonly, the multipass will, in open sky environments, you will maybe have maybe 1 or 2 meters error. But in a city cavern, for example, there are lots of buildings nearby, and this error can be accumulated to probably, I think, about 30, maybe some to 50 meters. Sometime in special case, it's very horrible. So this is a multipass. Okay. And the last one in the tracking parts I want to say is we commonly will introduce a lock detector. We call it lock detector to check whether the signal is in tracking or not. When you open your GPS or whatever receiver, they will give an indicator. Some is the signal strength about maybe 43 or maybe 38 to indicate how much is the signal be tracking, how level. Okay, so in the last parts, okay, for the time. Okay, for the last parts, I will tell you how to make parameters calculations. So if everything's fine, how to calculate the results. This is in this parts. Navigation parameters calculation. How to calculate the result. So if you keep up tracking, then you know the satellite is here, and you have this. You could get the frequency and the information from a satellite. So when you get the information from satellite, it's like look like this curve, like this one. We show you the data. For example, this one. This is the data you will get from the satellites. Each one is a 1 bit. So because each navigation bits of the GPS L1 signal, this is 20 milliseconds. So each point here, each point is only 1 millisecond. So each consequence 21 milliseconds means a navigation bit. So you can read this data as 1 1 0 0 1 1 1 etc. You will get the data. So we call this one is bit synchronization, because you need to find the bit step by step. Okay, so when you got the data from the satellite, you will get it like this form. Okay, so we need to guess the boundary of where is the data beginning. So the easiest way is use the transition. Okay, the transition bound. That means the data is from positive to negative, or maybe from negative to positive. We think it is the beginning of a data bit, of a data, navigation data, a nav data. We think it's the beginning of a nav data at here. So from the beginning of nav data, we can decode each message step by step. And sometimes we also, because of interference of noise, commonly we can use the histogram methodologies to process it. And if the data has errors, we have special parity check methodology. This is a kind of like a Hamming parity check code to make a parity check to the data. And the future, I mean, compared to the GPS, but nowadays the technology use some forward error corrections, for example, LDPC, and maybe earlier for the BCH, a lot of FEC technology. It's forward error correction. That means when you receive the data, not only you know the data is error by parity, but also you have a capability to recover the original information. Then that's similar as, for example, if you go along the road, you lost, for example, $100. You dropped it in the street. You're missing some data. Okay, but when you're to the destination, you can automatically restore by the data, and you can recover the $100. I think the error correction is like this way. For the parity, it just let you know you lost the data, you lost the note. But for the error correction, not only let you know the data is lost, but also to recover it. So this, for example, the FEC technology is using in nowadays signal structures. Okay, this is the parity check, and after the synchronization, we will decode by each frame. For example, the each in the GPS, each is 6 seconds is called subframe. So we can decode the data subframe by subframes, this clock, ephemerals, allemanic, and etc. Step by step by the frame. Okay, each frame is beginning with a preamble. It's 10001011. Each frame is beginning with a preamble. So it's make you possible to decode the data. Then after the preamble, you can decode the data. For the GPS, you can buy the ICD interface control documents. And for the GPS, you can find ICD 200. This is the documents of what each bit is meaning. Here you can decode all the Kaplan parameters I've mentioned before. For example, the time, the eccentricities, for example, the inclination, the argument of perigee, and so on, the semi-major axes. And after you get the data, and you can also get the time information by the T count. For example, the GPS time will be announced to you by the T count. For example, the satellite will say, okay, this is time 0, and this is time 1, and this is time 2. When you receive this signal, you will know, okay, so what time it is, what time it is, and then you can know what the corresponding time. We call the GPS time. You can know the GPS time by receiving the data from the satellite. And after you receive the time, your local time, you can track how much is the signal propagating by know the delta time t. For example, if the set time at transmit time tr, and for you are receiving the signal at rr, so then you will know the difference of the propagation delta t. But it is called pseudo range because your time is incorrect. You have a delta clock error. The clock error is unknown. Actually, this t is inside this clock error. And after this one, you will calculate the pseudo range by the information. After you can, when you get, for example, 4 different pseudo ranges, for example, in this case, after you get 4 pseudo ranges, then you will calculate x, y, z, because we will get 4 equations. For example, what you know is D1, D2, D3, and D4. This is what you know. And then by these 4 equations, you will solve x, y, z, and delta t. X, y, z, and delta t. So this is 4 known parameters and equations, and this is 4 unknown parameters. So by 4, you can make the calculation. So this is the pseudo range calculations. Then by these 4 equations, x, y, z is set from satellite, and x, y, z from the users, you will get these results. But there was problem because this equation is very hard to make solution. It is because this is a non-linear equations. What we need to do is to make it mathematically linearize the equations so in a matrix format, and finally we will get this equation. The delta pseudo range equals to the delta x, and you use iteration method, you will get the final x. That is x, y, z, and t. Okay, and finally, when you make the receiver, when you make a positioning, you can still use, for example, the Kalman filter and other filter method to make the positioning seem to be more precise and more smooth. Commonly, the results from your cell phone is the result after Kalman filter. So you can find that the result of the left picture to the right picture, right figure, you may see that the arrow will shrink after the filter. Okay, so this is mainly the principles of the GNSS receiver. I think, Dr. Abrahami, we can take a few minutes rest.
Yeah.
Is that fine?
Yeah.
Okay. During the rest, I can still make a Q&A. We can answer the questions. Have you anyone have questions? Also see the chat.
Yes. Yeah. In chat.
Oh, sorry, I lost the previous chat information because my net was a problem. If you write down chat information, you can still write down it.
Yeah. Even with defined PRN code,
Yeah.
you will still have 2046 search results.
Oh yeah, sorry,
Yeah.
my name is Chuck. I asked this question. I wanted to know that even with the PRN code, you still get 2046 searches.
Yes. I will draw something. I think you can see it. For example, this is input PRN code. For example, this one. And this is, for example, this is input. And if you want to search the code, I think for the PRN code, only when these two is exactly matched, you will get a peak. But you don't know the pattern. You need, for example, the move to the left or to the right to find the proper prediction. So because you don't know where is the input, the phase of input, I think probably it's you can make guess like this one. So you need to move step by step to this one. So this step is 0.5 chip. So totally, we are now to guess the chip of the PRN code. We are using to move to let the two chips match each other. So there are 2046 possibility of the position. Okay, so this is the 2000 means, not to get the chip, but to get the position of each chip. Is that clear?
Yeah. Is there any question? Please raise hands if you want to ask a question. Please raise your hands if you want to ask a question, or through the chat menu. Okay, Dr. Chan, then we can move to the next part.
Okay.
We have a question at the end if there's any.
Okay, so in the next part, I will tell you about the evolution for the accuracy of the GNSS. Commonly, we actually have two words. The first is accuracy, and the second is precision. So this is two words. This is two words. So I always give some pictures for you. For example, you see in the left and the right one. If you get the results from these two figures, you think which is better? Left or right? Which is performance better? So the left one has more accuracy, which means how closely the measured value is to a true value. The right side one is called precision. It means the degree of the reproducibility or agreement between a repeated measurements. Okay, so here you can see we call this one accuracy. And let me see. We call this accuracy. How much is the distance from the center? We call accuracy. And how much the error is distributed? We call it precision. And so actually for the accuracy or maybe precision, you need to make it clear what are you really meaning to the trueness, or what are you really meaning. There was a fact, a methodology to consider accuracy and precision at the same time for the CEP. We call it for CEP, called circular error probability. That means CEP means in the center, this is the true value, and you draw a circle to let 50% of the position in. So how much is this error? This error is we called circular error probability. Also, we can use some DRMS corresponding to 68% sigma standard deviations, 2 DRMS, 3 DRMS as the results. This is commonly for the accuracy of the this is for GPS results, how much accuracy you can be achieved. And also we will show you the result of the BDS. Okay, the BDS results. We will show you that the BDS results in the January of 2019. We will find that from this result, it's non-official results. And the Day3, the results show that the Day3, the new signal, commonly better than 10 meters. For example, you will see the accuracy of the B1C is about 2 meters, and for vertical, 5 meters. Okay, and for another frequency B2A, so it is 3 meters, as well as this is 8 meters. This is the average results in the stations all over the world in the 2000. And nowadays you can find more higher accuracy compared to this result. So actually the availability means the navigation system, how much is the percentage of the time is the service is usable. We call it availability. That means commonly accuracy, satellite number, mask angle, satellite outage, and GTP also is the factors that will affect availability. So we will show you some interesting pictures. This is an old one. This shows the availability of GNSS in the year 2014. And you may see something that almost all availability is more than 99%, if it's in the white color. But some yellow one, this is more than 95%. This is availability. That means you can have the receiver output as the official document. For example, if you are here, then probably at 95% your receiver is, for example, about less than 10 meters. But in the remaining positions, your receiver is 99%. You can have a 10 meters error. You see, this is the picture of the same time of the GPS. Also, you can see in some points, it's 95% availability, but the remaining is 99%. Okay, so that means each satellite systems has limitations. They only have some place that is about 95% of availability. But when you combine these two together, you will see, for example, this is GNSS plus GPS. If you're using GNSS plus GPS, GLONASS plus GPS. You will see better performance than GPS and GLONASS only. So I want to say that if you use multiple GNSS systems, then you will get a better performance. I also find that in the recent, let me see, in the recent results, this is the picture I take a snapshot, the availability snapshot at year 2020 May. I think about probably 5. Am I right? 5 days early, right? 5 days early. This is almost real time. So you may see this is the result is Beidou, and the left up, this is Beidou. The left down, this is the GPS, and the left right, this is GLONASS. Okay, okay. The number is lower. That means the better. This is the DOP. I think GDOP distributions, PDOP distributions. The more when the level is the 102 is the better, and the upper one is not is bad. So you may see from this picture, we say the BDS and GPS, they have similar, I think, similar availability. GLONASS a little bit worse than that. Okay, so this is availability show in the May, show in this May. Also, as our test results, for example, in the Arabic region countries, anytime at least about more than 10 Beidou satellites can be received. This picture shows how many satellites you can receive in the 22 number states of the region of living states. Okay, some countries you can see you can receive about 10 to 15 satellites, and some is a little bit lower for 6 or 7. This is the current Beidou state. Also, we make tests about Beidou receiver in the 2019 February, about one year early. You may see we tested in Tunisia. We have a GNSS Beidou GNSS center at Tunisia. So if in Tunisia, commonly there have about 10 Beidou satellites will be always available about in the Tunisia. So these figures show you which satellite is corresponding to which period during Tunisia. Okay, so this picture I want to show you that, as I think last course somebody asked me about the performance of the BDS. I think these pictures will give you the results of how is the performance of the BDS system. And the third one is about integrity. Integrity is criteria to measure that how to trust can be placed in the correctness of the information. So that means if the receiver give you output, is this output valid? Is it true? Is it correct? If it's not true, we need to warn the user as early as possible to let the users don't use the system. The integrity is very important in aviations. For example, the civil aviations, when the aircraft is landing, sometimes the force value will be very horrible. So it's the system needs to be with a very high integrity. If there are errors, they need to tell you more early. So to make integrity, for example, this is the real results, and this is the measures results. In some case, so if there has error, the receiver or the system may tell you that this alarm, false alarm that make you to have errors to predict okay, the output is not trustable. So that is the purpose integrity. So the receiver itself can also be used for integrity check for this RIM, called RIM, Receiver Autonomous Integrity Monitoring. So it's if you have over-determined solution over the receiver, it provides you capability. For example, if you use 4 satellites to make position, but if you can see 5 satellites, so the 5th satellite can be used to detect a failure. For example, in this case, if the satellite vehicle number 3 is failed, okay, so we can use the different groups, 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 4, 5, etc. So then you may find if the satellite vehicle number 3 is involved in the receiver, it will be error. So that means the error is equals to S equal number 3. So we can kick this satellite out. We can let the satellite don't involve in the positioning. Okay, so this is the signal performance about the receiver. So commonly, you need the availability to be, you may see in this one, 99% to 99.999% for the civil aviation. This is the evolution index for the GNSS. Okay, I will check about anyone has questions. The detectors.
Please, if you want to ask,
okay,
raise your hands.
Okay, so if no questions, we will continue. We have another chapter.
Okay.
Okay, wait a minute. Share screen. Okay, then we will talk about some status and trends of the GNSS development, the detail, and also with some regional and augmentation systems. So we'll show you that the first about GPS. The traditional GPS, I think like about this one, currently GPS. And then the GPS is in its, we call the modernization program. So the modernization program means the system is trying to increase the system capabilities and increase the defense and civil benefits. So in the policy of the United States is to maintain the US leadership in the service, province, and the use of satellite navigation systems. Okay, so the modernized program is trying to improve this one. So the military, the modernized program to protect the service for its US and allied forces, and also prevention from adversary explanation. And also for civil, it's preservation of civil user while providing enhancements. But that means when you use the system, you can still use the old version. I want to talk something interesting for the GPS. This is what happened in 2019 in the June 20 to 21. You may find that the GNSS system signal globally, the system is in abnormal. We see the something in the red dot. You see the red dot, red dot here. For example, red dot. all these red dot stations report abnormal of the GPS systems. What is abnormal? That is GPS L2 signal power is suddenly increased by maybe 3 to 5 times more. You may see the picture. This is the average commonly. And suddenly the signal is increased. Suddenly the signal increased. So what would happen? Actually, that is because Iran shot down the US MQ-4 Neptune drone in the June 20th. And Trump approved the plan of air attack on Iran that day. It was scheduled at the 4 a.m. in the June 21st. But I think later he withdrew. But before he withdrew the order, the GPS was make preparation for the attacking, so the signal power is greatly increased. For preparation, because the satellite, you need to tell satellite to make preparation, so the signal power suddenly increased. And not only in Iran, similar things happened in Syria. I think maybe the friend from Syria know it. The GPS signal also increased before the air attack. For the GPS, the modernization program, it included the GPS 2R and the 2F, and then to GPS 3. Now we have two satellites of GPS 3 in space. So the latency accuracy improvements, they want to make some improvement in the accuracy in the early. It is already completed in 2008. They want to have more monitor stations intended from 6 to 16 stations, and they also add 10 operational GPS module site to increase the accuracy. Okay, this is the snapshot of all the monitor station of the GPS distributed over the world, and also they have some OOCS, that means station, and the observation station, control station, their improvements. And also they have the architecture evolution plan to make the system evolve step by step. So they launched the early orbit, abnormal resolution, and the disposal operations. This handles the GPS system outside the operational constellations. So when the GPS is out of their monitor station, so it is still possible for the system to monitor the satellites. And also they are still upgrading the next generation operational control systems to provide to replace the X-command segment, and also to support the new infrastructure and the new GPS 3 satellite. So this is the next generation pictures. And so from this stage, the first GPS is block 2A to compare to the first generation, it's block 2. And then after it is block 2R replacement. The replacement, they have launching to the onboard clock monitoring, and they were mainly launching in 1997 to 2004. And block 2RM, this is means modernization. They add a second civilian signals and the 2 new military signals. So it's make flexible power levels for military signals. And the second signal that the traditional we are using L1, CA code L1 as the main signals for our cell phone is received. But now the GPS also broadcast the second civilian signal called L2C. They provide better performance. This is the L2C signal of block 2R IM satellites. And this is L2C signal on the block 2F satellite. No. And recently, they have launched the block 2F GPS satellite, which has new the third surveillance signals, L5 signal, and each satellite can serve for more than 12 years, and also have more accurate ultimate clock. This is the L5 signal. And then recently, so from 2016, the GPS began to launch a new generation called Block 3 satellite. So it adds a fourth surveillance GPS signal, L1C, and also it has enhanced signal reliability and has laser reflectors, and also it has a 15 years design lifetime, and that means the satellite can design for working for 15 years. It's a very long time for satellite. It's gradually, it's from block 2A, block 3A, and then it will be upgraded to block 3B and block 3C, and step by step. So totally, the GPS 3, block 3, has many interesting structures. The first is it has a, we call a directional antenna. This is called directional antenna. This antenna will sending the signal to specific region, region 1, region 2, specific region, and then in this region the signal is augmented and to have better performance. And then in the L1 frequency, there was many satellite signal combined together. That makes the users can have many choice as you like to find appropriate signal. And this is combination. So also it has crosslink. That means the satellite can communicate with the satellite to sharing many information between them. Also, this system is also used in Beidou system. So after the signal, more and more signal will be added since block 2A, block 2M, block 2F, and block 3. More and more satellite signal. Even using more satellite signal, you will have better performance for example, aerospheric correction and many other benefits. But it's need more expensive equipment if you're using more satellites. So commonly, when the generations increasing, the solar range area is decreasing. For example, in the year 1996, the area was 3 meters, and in 2000 to 1.5, and nowadays we think it's only about 20 centimeters for the accuracy of the GPS. And then I talk some about the GLONASS. The GLONASS, actually, the deployment of the GLONASS began in Soviet Union in about 1976, and the constellation was completed at 1995. But you know, then the Soviet Union has a lot of problems, and so in the 2000s decades, the system is under maintenance. Without maintenance, it's degrade. So under Putin's presidency, the restoration of the system was made a top government priority to increase. So in the October 2011, the full optical constellation with 24 satellites was restored. Actually, GLONASS is very good, and then I think the Russian bankrupt, so probably I say bankrupt, but they don't have money to maintain the satellite, and then now it's begin to make recover. Okay, this is the picture show you how many satellites is in the sky, and this is 9 and 26, and then no money, and then decrease to 7, and then increase again. So this is a history, progress of GLONASS system, and then also GLONASS, their control station is distributed over all the Russian national land. So because Russia is very big, they have lots of land to place the monitoring station. And also the constellations, the parameters, and they have different types of the satellite GLONASS M, GLONASS K1, GLONASS K2, etc. And also the GLONASS has currently this is GLONASS signals and expansion of the signals. And also the GLONASS is also make its modernization from the GLONASS to GLONASS M, GLONASS K, and GLONASS KM to add different satellite signal into the system. I'm gonna something. But remember the GLONASS has a little bit difference as the GPS coordinate system I mentioned before. So also it has about some data in X, Y, Z corresponding to the international reference framework. And this is the PDUP shows in the year 2012. You may see sometime is very bad, very bad. And I will see another thing. I will see Galileo system. It's quite interesting. Galileo actually was built, actually hoped to build by European Union and the European Space Agency in the 1998. When they decide to have their own satellite system, because the U.S. government don't agree this project. So until early 2002, the European Union decided to fund to the development of the Galileo system, and this system is very interesting. The GPS, the Beidou, the GLONASS, they also have civilian users and the military users at the same time. But the Galileo systems mainly focused on the civilian users. They provide civilian users and commercial users. So they designed to be finished, the system designed to be finished at 2008. So actually the constellation, they hope they can have a 30 in-orbit spacecraft. So this is a satellite, the picture of a satellite on constellations. This is the hydrogen atomic clock and the rapid atom clock. So they provide 5 services. The first is for open access, the second for commercial, and for some encrypted and safety life, 5 different services. But actually, as far as I know, seldom people focus on the commercial and the public regulated. And also, this is signal systems. It's very complex system, mainly on binary of carrier, so that BOC modulations, because they need to share the spectrum with the GPS system. You may see that they are sharing the spectrum with others. But the Galileos, they plan to be finished in 2008, but they always delay. You know that European Union always delay. And they have launching 4 in-orbit validation satellites at the year 2013, and then they have initial Galileo service, and now they hope they can have fully operational capability in year 2020. I'm not sure about that, but they said to be 30 operational satellites and completely ground infrastructure. They hope at end of this year, they hope they can have provide full services. This is the initial test of the positioning with the Galileo systems. I will show you that, for example, the horizontal accuracy is in 8 meter and the vertical in 9 meter. 8 meter and 9 meter. And time accuracy is 10 nanosecond, and the search and rescue beacon can have 2 kilometer accuracy. This is a Galileo segment, a ground control segment distributed all over the world, and this is the Galileo initial validation vehicles and their future development. And the first part I will talk about the Beidou. The Beidou, actually, the name of the Beidou is named after the Big Dipper constellation. You know, Big Dipper is kind of constellation look like 1, 2, 3, 4, 5, 6, 7. We call it Big Dipper. That constellation like this one. This is called Beidou. In Chinese name, we call it Beidou, and in English we call it Big Dipper. It's designed by, original idea was convinced by a Chinese scientist called Chen Fangyun, and its co-workers in 1980s. And after it, they began to make practice. In the year 2000 to 2003, there was experimental Beidou 1 with 3 satellites. And by the year 2012, it's Beidou 2 to step to global coverage. But then by year 2020, sorry, this is Beidou 3. Beidou 3 in global coverage. So the Beidou 1 is an experimental regional navigation system. It only to use 3 satellites, mainly 3 satellites and 1 backup. Actually, there are 4 satellites, but 3 is main and 1 backup to give you position. Only 3 satellites, but only serve for Chinese mainland area. So, and also it is an active positioning technology, not a passive technology. And the Beidou 2 is not an extension to existing Beidou 1. So it has 14 satellites, which has 5 geo satellites and the 14 satellites for Beidou 2, 5 geo and 9 non-geo satellites. So the Beidou was using the Chinese Geodetic Coordination 2000, and this is the information. This is the information. And the Beidou 3 is a constellation. This is constellation of the Beidou 2. You may see it, and this is the geo satellite. This is the geo satellite, and this is non-geo satellite. Non-geo satellite. Distribution constellations. And for the non-geo satellite, this we have specially called IGSO constellations that mainly move around. It's like 8. The track of the satellite is like 8. It's moved like a geostationary, but mainly provide service for the Asian Pacific area. Okay, so we took the picture of the Beidou 2. You may say mainly satellite is geostationary 1, 2, 3, 4. Oh, where's G2? For example, G2 maybe. Actually, there were 5 satellites here, and this is for IGSO, and this is for MEOM. This is distribution of system mainly for Asian Pacific area, for the Belt Road countries, mainly for this one. So the next stage called Beidou 3 is actually is a globally coverage, but it still have 5 geostationary and 3 IGSO. I think these 2 mainly for Asian Pacific region, including China. and 27 remaining satellites for global coverage. This is for global. There were 2 surveys. The license service mainly for military and the free license for civilian users. And it provides about 10-meter accuracy and 20 nanoseconds time and 0.2 meter per second velocity accuracy. So after deployed, the Day3 constellations should be look like this way, and this is also GEO satellite, and there were some inclinations and others. This is for more non-GEO satellite for global coverage. The latest news shows the last Day3 satellite will be launched in next month. I just got information from the office. I will show you a video for the Beidou satellite system. I'm not sure you can hear it, but not. But if you can hear it, please send me a chat.
The video without sound. Tijan?
ما في صوت مسموع. ما في صوت.
Dr. Jan, there's no sound.
Dr. Shiani, do you hear us?
Okay, hope you enjoy the video. So it's it's little bit noise. Okay, yeah, I'm not sure about the Zoom. Sorry for that. But they have subtitles. Okay, so this is the where is my point? Okay, okay. In the last, I will talk about some regional and argument systems. Except for the 4 main satellite systems, we still have the regional and argument system from other countries that provided regional support and argumentation support of the satellite navigation systems. Commonly, we get this one. You can probably see that this is WAS. This is from American. sorry, the US, and this Ignis from European Union, and this is SDCM. This is from Russia. Where is it? Yeah, this is Russian, and this is Gagang. Sorry, now they called it NAV-IC. Gagang NAV-IC. This is from India, and this is MAS. This is from Japan. So this fourth system is we call argument system. They were sending the information to not for navigation, but to enhance the navigation system. Okay, so for example, the WARS from the United States, it is because WARS is deployed by the FAA, the Federal Aviation Administration, to augment the GPS to improve its accuracy, integrity, and availability. Is set mainly to enable the aircraft to rely on GPS for all phases in flight, including precision approachings and to any airports even without coverage area. So they just provide information for this. So the WARS is just sending the argument system, some information that to eliminate the errors in the GPS. But the WARS system only provides service for the United States. Remember, if you are in every countries, you cannot use WARS. WARS is not like GPS. GPS provides service for all over the world, but the WARS only provides support for Americans. So that is WARS. And for in the European Union, this is for we call Ignis. That is European Union's geostationary navigation overlap. So that is, so they are just provided by the ESA, the European Space Agency. Similar as the VARS, but it's made by European Union. Provides service for European Union because the European Union users cannot use VARS, so they just use Ignis. And for the Ignis systems, this is their operational phase since maybe year 2010 operational phase. And Ignis provide for mainly for European Union, and provide this is how much the coverage it can provide it. You know, something. And the QCSS, this is from Japan. It's start from year 2002. So it's just to increase the performance by JAXA, by the space agency of the Japan. It's because the Ignis cannot be used in Japan, as well as the VARS cannot use in Japan in the East Asia area. So no one can use enhancement system. So the Japan set up the QCSS system to provide improvements of multi-constellation GNSS. Okay, so this is the picture of the QSS. This is the track point. Okay, this is mainly covered in Japan. Okay, this is the satellite of the QSS. Okay, this is the picture of the satellite orbit of the QSS system. You know something. And last, we will see. Okay, after the correction by QCSS, it can increase the accuracy from about 5 to 10 meters to 1.6 meters. To decrease the system. For example, if using GPS, the error is about 5 meters to 10 meters. So by using QCSS, it can decrease to 1.6 meters approximate. Okay, so that means this is the accuracy. This is the accuracy of the users. I know something, and this is the performance. For example, you will see that this is the accuracy of the availability of the GPS only, and the accuracy improvements of the QCSS. Ignore something. Because time limitation, I just ignore something. And the last, we will show you about the systems from India. This is called Indian, called Gagan, or later called RNSS. It's Indian Regional Navigation System, and last we call them NAV-IC. So it is a GPS added geostationary argument systems. So they're similar as a VARS, but they just place many satellites on the geostationary. It's similar. So the Gagan, okay, NAV-IC is in two phases. The first is technology demonstration, and then final operation phase, since from 2016. So recently it has been completed. It provides service for India. It's called Indian Regional Navigation Satellite Systems. So this is its architecture. So its constellation, they have the 3 geostationary satellites and 4 inclined geostationary satellites. They are all launched, and in 2014 they have published the documents for how to use the systems. So they hope they can use the systems in the L1 and L5 frequency. And the last one is the augmentations from Russia. It's called SDCM. It's by the Russian Federal as a component of the GLONASS. It's similar as the VAR systems of the GPS. The SDCM is the augmentation for the GLONASS. It has 3 geostationary satellites to control, similar as VAS. It has also have a reference station network to calculate the error and the broadcast to the users. So this is the system from Russia. And also in China, the Chinese government has set up the satellite augmentation a bit later, but the China government has set up the ground augmentation system. They have set up more than 2,200 reference stations, only served for Chinese mainland, and also its accuracy, you can wide area can be meter or decimeter levels. For regional, they can have centimeter level, but for post-processing, the system, argument system can have the millimeter level accuracy. Okay, so I give an old picture for this one. You may see in the how much constellations, how they are fully operate, and the coverage status and the civil spectrums at this table. Okay, so the time is limited, so sorry for a little bit delay. So okay, so this is for today's lecture. So any questions? First, I will check about chat.
Thank you, Dr. Tian. There's a question in the chat, and we wait for people to raise their hands for more questions. This was the question.
I will see. Okay, PPP taken to delay. How PPP? Okay, okay. There were 2 words. I will see. Oh, so many questions. So the first is the difference about the PPP and RTK. Actually, there was a 2 words. The actual RTK. The RTK is called real-time kinematics. It means that you will have a reference station. That reference station will broadcast the how much error is the satellite is, and then for a rover, another satellite, you can receive this correction. You can receive a correction from a nearby station. We call it call station or base station. Then you will know how much is the error in the system, and then you can comprehend this error to have the high accuracy position. Commonly, an RTK receiver can, for dynamic users, can have accuracy about less than 1 meter. Similar like you using WARS. So WARS is kind of reference station in the space, but for RTK is a reference station in the ground. As let's mention, the Chinese people has made more than 2,200 this kind of reference station is by RTK methodology. And for the PPP is somebody is for precision point position. That is different as RTK, but because PPP don't need a reference station, it just download the correction of orbit. They just tell you, for example, someone will calculate how much the error is orbit is. They do not need to download. They just need to download the correction information from a globally distributed network, not by a reference station. So this is the difference between the PPP and the RTK. Apart from missile system, so I can't understand what is the second question mean. Apart from missile system center and with creation of a lot of space force, try to improve cyber risk. Sorry, I don't understand what the second question mean.
Just a comment, I think.
Okay.
We have more questions.
Any more questions?
Meanwhile, I
Okay.
would like to remind all participants that we will meet Dr. Jian day after tomorrow, and Thursday at the same time.
Thursday same time. Yes, Thursday same time. Okay, if no question, thank you for listening.
There's question. Then let me, Dr. Jian, thank you a lot for this very enjoying lecture. We interested it very much. And at the name of all participants, we would like to thank you, and we hope we will meet you in good health next Thursday at the same time. Goodbye.
Okay, bye-bye, see you.
See you. Bye.